Oh, right, and I have to start there's too much technology going on these days. I have to start the timer because the camera, the high definition camera, will only record for 30 minutes. Okay, I can try. But today we talk about right. Good. We're recording. Yes, we're recording. We're recording with that camera. Everything is good. So now we're actually going to talk about a particular problem, which is not just, you know, some weird abstract problem. It's a concrete problem. It's a concrete problem for you because it's actually your first homework assignment. Your first homework assignment is not like the other homework assignments, because it's only one question, and it's hard, but it's not super hard, and it's there to because I'm supposed to give you something back back before the drop date. So the idea is there will be a tutorial on Friday, which will be sort of how to do this stuff, and then it'll be due a week from Friday, so I think on the 14th at midnight. So next week there will be 2 office hours on there'll be 2 office hours, I think, on Thursday and Friday. But the tutorial this week is for this homework. The tutorial next week will be for the homework that's due the week after. So please don't go to the tutorial and say, I looked at this the last minute, I can't do the homework, because the office hours are for that. So let's talk about, what's this problem we're going to talk about today? So it's going to be sort of a flow from the stuff we were talking about on Monday. That was only 2 days ago, which was hard versus easy, or well, impossible versus impossible. We sort of discussed that. Then we got into this hard versus easy stuff. And I told you that one of these problems that I gave you some examples of problems that are Eulerian cycle is easy, and Hamiltonian cycle we think is hard. We don't have a polynomial time algorithm for it, and we've been looking for almost hundreds of years. And there are lots of other problems which turn out to be equivalent to Hamiltonian cycle. Okay, so we're going to see a bit more of that today, but we're also going to start getting into this first paradigm of algorithm design, which is divide and conquer. Most people in most classes, when I saw divide and conquer, they're like, oh, merge sort, quick sort. And like people think, oh, this is super easy. You use divide and conquer for easy problems. Well, so in order for you not to think that, I'm going to teach you divide and conquer on this insanely hard problem, which I've told you we don't have a polynomial time algorithm for. And actually, what I'm going to teach you is not polynomial time. It's just going to work really, really quickly in practice. And then we're going to get into some. Okay, so where did this problem come from? Well, so let's go back into sort of the history of graph coding. So we said that the graph theory started with Königsberg. By the way, I remember I asked you to remind me about exclaves. So Königsberg is now Kaliningrad. It's an exclave of Russia. So this will come up in just a minute. I've looked at A1. This is any requirements on the running time of the code. No, but if you do it brute force, it won't stop in your lifetime. So I'm going to show you 2 versions for coloring Nova Scotia. Now you can brute force Nova Scotia, right? Like it's only 18 counties, so you can. And so if you try all the possible, okay, we'll get into it. If you try all the possible 3 colorings, it's 3 to the 18. That's not actually very much. It's like 400 million or something. Your computer will just burn through it. The map on the assignment has 42 regions. If you try to 4-color and you try all the possibilities, it's 4 to the 42. It's like 10 to the 26, 10 to the 25, something like that. So it's not going to stop soon. So you can't just use the super simple, like try everything. You have to at least be a little bit sneaky. Okay. So graph theory got started, and then so it was in I just checked the dates, but I forget. It was like in the 1800s, in I think 1854 or something like that. There's this. He was actually also a mathematician. This guy Francis Guthrie, I think, wrote to his brother, who was like Frederick Guthrie or something like that, who was studying with De Morgan. Who is, if you studied De Morgan's laws in propositional logic, this is Auguste De Morgan. And so he noted this thing. He said, I just noticed I can color all of the counties of England, or yeah, I think just of England, with 4 colors, such that no two that share a border of positive length, which means they can touch at a corner, because a corner actually has 0 length, right? It's just a point, but a line has positive length. So so if they share if they share a border, they can't be the same color. They said I can color it with only 4 colors. So does anyone remember, like when we were children in geography class, we had to color maps. And actually, I remember reading in a book, somebody observed, like, yeah, up until about like high school, that's mostly what your geography mark was, how neatly you could color the map. I could color fairly neatly, but I always lost my pencil crayons. So it would have actually been really useful to me to have a good algorithm to give me a 4-color, because then I would only have needed 4 different colors. Except you need, like, they have these silly rules, like blue for water. Okay, so he said, like, is this a coincidence, or can you always do this? So looking at the counties of England, you'd think, yeah, that doesn't seem to be just a coincidence. There were 39 counties back then. They've been merged since then. There was a conjecture that got published twice, once by, they're not sure which brother, because they both have the same initial. And so it was just listed as F. Guthrie. And then it was published again by De Morgan in like 1860, I think. And the conjecture is, yes, you can always color a planar map, and it doesn't actually, like, if it's on a sphere, you can always project it on a plane. You can color a planar map with 4 colors. Now, this exclave thing gets a bit complicated, because an exclave of a country is a part that doesn't have to be connected, and you can fairly easily come up with examples. If you're allowed to have exclaves in your map, and the exclaves have to be the same color as the country, then it doesn't work. So I'm not going to use the new markers yet, because you should be able to see this. Because right, so if we have, let me think. So this is my map. And so this is country A, B, C, D, E, A. Can you read that? I hope I can read that on my screen. Yes, okay. So I claim that this cannot be 4-colored, right? So this is an exclave of country A. And the reason this cannot be 4-colored is C, D, and E are all different colors, are all adjacent to each other. So they have to be different colors, right? So this has to be, so these have to be different colors. B is adjacent to all of these. And so it has to be a different color. So you need 4 colors for B, C, D, E. But then A is adjacent to B and C, D, E, right? So now you need 5 colors. So if you're allowed to have exclaves, then things get complicated. Now, exclaves, it sounds like Kaliningrad is an exclave. It's Kaliningrad Oblast. So then you have like, so for example, there's an exclave of Italy in Switzerland. There's an exclave of Spain in France. There's where? Like their overseas territories. So I was thinking of making a color the world map, but then I got it. So for example, like French overseas departments are actually considered part of France. So close to us, it's not exactly an exclave, but if anybody's been to Saint-Pierre-et-Miquelon, it's like a few hundred kilometers northwest of us, I guess. Uh-oh, the audio is important. So yeah, Saint-Pierre-et-Miquelon, I went there. There was a conference in Newfoundland. I was living in South America, and it has the same plugs as Europe. So I went from the conference in Newfoundland. I spent a few days on Saint-Pierre-et-Miquelon, so I could charge my razor. But everybody there's an exclave which is really big, which we don't usually think of it as an exclave, which everybody should. So just to make sure that people are awake, tell me the biggest exclave you can think of. Yes, Alaska. So this is, I've never actually, until I was preparing this lecture, I never actually heard of Alaska referred to as an exclave, but I think it is. Okay, so wait, somebody else had an, yes. Okay, so we're gonna ignore exclaves. So there was this conjecture, and it ended up being sort of a key part of graph theory. Now, why is it graph theory? Because it turns out if you take I shouldn't have just erased that. If you take a map and you draw a vertex on each region of the map, and you draw an edge between two vertices if they share a positive length border, then the map can be k-colored if and only if the graph, the graph can be k-colored if and only if the map can be k-colored. Where the graph coloring says, if two vertices share an edge, then they can't be the same color. Now, if for every place that the regions touch, you draw an edge through that connection, then you get a multigraph. So vertices can be connected, two vertices can be connected with multiple lines. So for example, let's not talk about, okay, so in this example, if I had A, B, and C, then A would actually, the corresponding multigraph would be A connects to B twice. Okay, so it turns out that actually if you do this multigraph thing, then you get what's called the dual of the map, right? So then the graph and the map are duals from the map you can get the graph, and from the graph you can get sort of the map, in that it's up to topological equivalence. So it's like you obviously can't get like all the squiggly lines, but up to like, do people know what topological equivalence is? Like if you drew it on a rubber sheet, you could, okay, somebody does. Okay, good. So this isn't so important for us because we just care that if you can k-color the graph, the map, you can k-color. If and only if you can k-color the map, you can k-color the graph. And you don't need this multiple edges thing. It's not going to be important. This is algorithms, it's not topology. So this theorem, this conjecture hung around for quite a while. So I think around the end of the 1800s, he would prove the 5-color theorem, that any planar map or whatever. Any planar graph, a graph is planar if it can be drawn in the plane such that the edges don't cross. It doesn't, not all graphs, not all graphs are planar, and not all the drawings of a planar graph have to be planar. You can definitely make the edges cross if you want. But so it turns out they're doing some construction and they have air horns. I don't know if you can hear that. I hope not. They're also like cutting down a tree and running it through a chipper. So it turns out like when you do graph theory, there's this like graphs are planar if and only if they don't contain a K5 or K33 as a minor. So this, we don't need this. So we do need to know a graph is planar if it can be drawn in the plane such that the edges don't cross. Not all graphs are planar, but planar maps correspond to planar graphs. Okay. So anyway, this theorem hung around for a while, and it was eventually proven by Appel and Haken, I think in the 60s or 70s at University of Illinois. How could I forget? I stayed up late doing the homework. You can probably see when it got posted. Illinois Urbana-Champaign. Yeah. I was thinking, I can't believe, like, my brain just shut down. I was like, University of Illinois, University of Indiana, University of something starting with that. But yeah, of course it's Illinois. I think. Now actually this is kind of cool because Haken, so part of the proof was checked by his daughter, who is Dorothea Haken. And she comes up again in this course because she was one of the co-authors of the master theorem. And also she taught me third-year algorithms. So like a couple of decades ago when I was where you are now, except I was actually in a classroom. Then I was, except she was Dorothea Blossing by then. Okay, so, I got this out of order. I was talking about maps and graphs. Okay, so so they proved it, and this was the first time people used proved something big using a computer to run through lots of cases. I think it was 1,800 and something cases, 34 cases. And so they proved it exhaustively, and a lot of mathematicians were unhappy because they said, like, we can't actually check your proof manually. We don't really understand it. Is this really a proof, man? Okay, so let's talk about okay. If I give you a graph, if I give you a planar graph, and I ask you if it's 7 colorable, what do you say? Hands up, everyone who thinks you say yes. Okay, if I give you okay, so I should check the participants. If I give you 60 attendees, I paid for like the 500 attendee Zoom subscription because, okay, yes. So at least some people think you say yes. Okay. So if I give you a graph, if I give you a planar graph, now there are polynomial time algorithms to check whether a graph is planar or not. So I give you a planar graph and I ask you, is this 7 colorable? Like, can you color it such that each vertex is assigned one of 7 colors and no edge has 2 endpoints the same color? And I get, well, you say, I told you that the, yes, okay. So I just told you that you can 4-color. There's a 4-color theorem. And actually this, I will try to find the picture again. I'm trying to learn Czech on Duolingo. And one of the things was 4 colors that are definitely enough. 4 barvy úplně stačí. And so this makes it into Duolingo. So if 4 colors are enough, 7 colors are definitely enough. So if I tell you the graph is planar, then, and I say, ask you if it's 7 colorable, you say yes. If I ask you if it's yes, a 4 coloring is a 7 coloring. You just ignore some of the colors. Now, clearly, there are for any number of colors. If I don't tell you the graph is planar, there are graphs which require any number of colors up to the size of the graph. Because, for example, a clique where every pair is connected. So a 4 clique is planar, but a 5 clique isn't. So, for example, an 8 clique requires 8 colors. So, if I give you a planar graph and I say, is this 7 colorable? You say yes. If I say 6 colorable, yes. 5 colorable, yes. 4 colorable, yes. Now, what if I ask you is it 1 colorable? What? So there is an easy condition for if it's 1 colorable. I'm going to turn on the chat and see if anybody writes this. No, wait. So the theorem is the map is 4 colorable if it is planar graph. Yes, if it's planar graph is 4 colorable. Yes. So yes, only if there are no edges. Yes. Okay. If I give you a graph and I ask you, is it 1 colorable? If it's an independent set, so all the vertices are isolated, then the answer is yes. You can color them all the same color. So now let's talk about this. So what if I ask you if it's 2 colorable? So I'm going to keep my new markers here for moral support. So if I say, okay, let's see. Okay, is this graph 2 colorable? How do we tell? Well, we start and let's say we start here and we say, this is red. So all of its neighbors had better be blue. And then all of their neighbors had better be red. And then we get a problem because we say, and all of their neighbors had better be blue, but they're not. Some of them are red. So we get a problem. So this is basically just breadth first search. Maps, planar maps, yes. If you don't have like bridges and tunnels, so yes, if they're planar, no bridges and tunnels, then you can do this thing where you draw the vertex in each region and draw the lines, and those lines won't have to cross. So yes, the corresponding graph will be planar. So basically, you do this breadth first search. And either you get a 2 coloring or you find an odd cycle, right? Because this is 1, 2, 3, 4, 5 vertices, right? And so you can't color an odd cycle, which is like a triangle or something. You can't color it with 2 colors. So if I ask you about 4 or more, the answer is easy. You just say yes. If I ask you about 1, the answer is like also easy. You say yes if and only if it's an independent set. If I ask you about 2, you actually have to do a little bit of work, but not a lot. Now let's talk about 3. A1 adjacency to, yes. Oh yes, somebody noticed that I made a mistake on the adjacency list. Possibly I made more mistakes. I will check and see if this is the same mistake that somebody emailed me about this morning. It didn't actually affect my checking the solution. I don't really care how many colorings that map has. I just actually want people to try it and get some feedback and sort of get a feeling for what this course is. It's not going to involve that much coding, the whole course. But I want you to have something which is like, okay. So I just have to check and see if this camera is going to stop. Okay, so let's talk about, we have 43 seconds. Okay, so 1, colorability, 2, colorability is easy. Let's talk about 3, colorability. So 3, colorability is one of those problems we don't have a solution for, not even on planar graphs. We don't know how to do this in polynomial time. Like obviously we can do it, but you can just check all of the possibilities, but that is slow. So we're going to talk about, so can you get any faster? Can you get something with polynomial time? Nobody's ever found an algorithm with polynomial time for general 3 colorability. Okay, so we're going to stop and then we're going to start the camera again, because the camera, there's a law that says if cameras can record for more than half an hour, you have to pay tax on them as video cameras. So even though technically, physically, like the camera could record for more than half an hour, because I stuck like a really huge video memory card in it, but then in the EU you would have to pay extra tax on it. So the software stops it recording after half an hour. And yes, you can hack it, but then it voids the warranty. And yeah, I don't really care about the warranty, but I also don't want to hack my like. There should be a nice way to do this. Also, this way it breaks it up into nice thirds. Okay, so let's talk about 3 colorability. So this, it gets a little bit complicated. So nobody's ever found an algorithm for 3 colorability. Now I want to talk about I told you, oh, I have to start this again. Reset, start. Okay. Now I told you planar 4 colorability is easy. You just say yes. But general 4 colorability, so if the graph isn't planar, you don't always say yes. For example, if I give you a 5-clique, then the answer is no. So I want you to see that if you could do, so this will be the first time you sort of see real reduction, not a real reduction, but if you could do 4 colorability, then you could do not planar 4 colorability, then you could do planar or not planar 3 colorability. So notice that if you can do planar 3 colorability, it's not immediately obvious that you can do general 3 colorability. But if you can do general 3 colorability, planar 3 colorability is a special case. Somebody gives you a planar graph and says, is this graph 3 colorable? If you have an algorithm that works for 3 coloring any graph that can be, then you don't care that it's planar. And it will turn out later in the course that if you have an algorithm for planar 3 colorability, you can use it to get an algorithm for general 3 colorability. So this is getting a little bit, okay. So did I do this in the last class? No. So imagine that you have this graph, G, and you want to know whether G is 3 colorable. Okay, but you don't, but you have a magic box, but it doesn't, that will tell you about colorability of graphs, but it doesn't tell you about 3 colorability. It only tells you about 4 colorability. okay? But general four-colorability. Doesn't have to be planar four-colorability. Then what you can do is you take G and you create this new vertex V and you connect it to everything in G. Okay, so now this whole thing, you're going to call this G prime. So observe that G prime is four-colorable if and only if, which I'm going to write IFF because I'm lazy, G is three-colorable. Why? Because if G prime is four-colorable, then just take V away, and G has to have been, the remaining part of G is three-colored. Because if there were an edge which had two endpoints the same color, then there would be that same edge with two endpoints the same color in G prime, right? So if G prime is four-colorable, then G is three-colorable. Now suppose that G is three-colorable. Then G, this is all three-colored, and you just use the extra color for V. Okay, so this is sort of a super simple reduction. So note that this requires four-colorability, not planar four-colorability, because you can have the graph, and if you connect V to all the vertices, that doesn't maintain planarity. Okay, even if G is planar, G prime may not be planar. Okay, so for example, if you take is a K33 three-colorable? Yeah, I think a K33 is three-color. I think a K33 is yes, bipartite, so it's two-colorable. So if I give you a K33, which is well, K33 is right. If I give you a K23, right? So this is planar. So this is connected to here, and this is connected to here. Right? So these are two bipartitions, and it's a K23. So everything on this side is connected to everything on this side, and everything on this side is connected to everything on this side. Now, if I add another vertex, then I can't, then this becomes, and I connect it to everything else, then this becomes not planar. Okay, I think I just made, I should check that later. Okay, so you see how this is starting to get a little bit, should I use, let's vote, should I open the new markers? So you can see that this is starting to get a little bit complicated. You have one colorability, two colorability, you have planar, four call, and then planar five call. And so on and so on. So as many of these as you want. And this is also, you have like Eulerian cycle. And then over here, so this is sort of the click side, and over here on the boom side, we have planar three colorability. Can you read this? Yes, we have polynomial type. Now we actually don't know if they're polynomial time algorithms for what I'm listing here. We can't prove there aren't, but we've never found any. So there's planar three colorability. There's three colorability. People are saying yes, they can read that. There's four colorability. There's five colorability. Why? So if we know that, if planar three colorability is hard, three colorability is hard. If three colorability is hard, I just showed you that four colorability has to be hard. So this is stuff this is Clink. And this is Boom. To use the technical terms. Okay, so I just showed you the three colorabilities. If we can solve four colorability, then we can solve three colorability. The same argument says that if we can solve five colorability, then we can solve four colorability. Yeah, let's not get into the P and NP stuff. That's a bit much for the second lecture. Let's stick with Clink and Boom. That's nice and non-threatening. Now, also, what we have is Hamiltonian cycle. Now, the cool thing is, now notice that if you also get, if you wanted to, you could solve, if you had a magic box that solved three colorability, you could use it to solve two colorability. Right? You would just do the same thing. You'd add on another vertex. This would seem not to be very helpful because we know how to solve this and we don't know how to solve this. So it doesn't help to reduce stuff we can solve to stuff we can't solve. But if you had the magic box, you could definitely do that reduction. So I'm going to say planar three colorability is, if you can solve this, you can solve this, right? So I'm drawing the arrows this way because I'm taking an instance of this and I'm turning it into an instance of this, right? I had G, which is an instance of three colorability, and I turn it into an instance of four colorability by adding another vertex. We don't know if Clink equals Boom. Well, so some problems we know are hard. We just don't know if NP complete problems are. So this turns into this. Later in the course, what we're going to see is that actually you can also, you can go backwards, but not directly. What we're going to see is that there's this problem called SAT, and then there's a problem called 3SAT. And SAT reduces to 3SAT. And 3SAT reduces to three colorability, and also three colorability reduces to planar three colorability, and five colorability, blah, blah, blah. And also Hamiltonian path reduces to SAT, and 3SAT reduces to Hamiltonian path, and five colorability and whatever reduces to SAT. And so you get a cycle, so all of these things are equivalent. So all of these reductions work in polynomial time. SAT is the problem of determining whether a propositional formula, a Boolean formula, is satisfiable. That's for like the last part of the course. I'm sort of bringing this in now. So what I should have done is, draw those. So these blue lines, so planar four colorability, if you can solve four colorability, you can clearly solve planar four colorability. If you can solve five colorability, you can clearly solve. Okay, so this kind of, these blue lines you can figure out. Notice that it would be weird we would have found a solution to all of these if we could draw an arrow from anybody on this side to anybody on this side. So what you don't know, what is not easy are the red arrows, which are, this arrow is pretty easy, actually. It's just something you don't know yet. Okay, so those red arrows are reductions which are not obvious. The blue arrows are fairly obvious. The blue arrows you should understand by now. Okay, so let's get in so that we can actually talk about the divide and conquer part, which is what you're going to use for the homework. Yeah. So this is like if you've done Boolean, you've done propositional formulas, right? So it's not, you can think about like, how would you write a formula that says, which variables would you use and how would you write the formula that says a graph is not three colorable, or that says a graph is, it says a graph is three colorable. You'd have to like write down these variables and say, okay, then each vertex must have one of these three colors, and no edge has two endpoints of the same color. So if this is red, then this is not red. If this is blue, then it's not actually that hard. Okay. So this is the diagram, right? Divide and conquer. So let's talk about, so let's talk about three coloring Nova Scotia. So this is how I get this reputation for brutality. These reductions are all working in polynomial time. Reductions don't actually, all the reductions you're going to meet in everyday life are going to work in polynomial time. You can still consider reductions that don't work in polynomial time. That's sort of now the new style for these things called fine-grained complexity. We may get to that in this course if okay, but for right now, just assume most reductions, like general everyday reductions, work in polynomial time. Okay, so I was saying this is how I get this reputation, because last year I taught people that three colorability is it's hard. We don't have a polynomial time algorithm even to tell whether a planar graph is three colorable or not. So to tell if there are 0 three colorings or 1 or more three colorings, we don't even know how to do that quickly. And then as a homework assignment, I said, okay, now here's the planar graph corresponding to the map of the counties of Nova Scotia. Count the three colorings. Tell me actually how many there are. Told this dividing coloring problem. Yeah, so now I'm going to tell you, why am I doing this only on planar graphs? So planar graphs have this nice property that they have something called small separators. So it means that if you have a graph on n vertices, then you can choose a small number of vertices. So what is a small number? A small number is, I'm just going to make sure this is recording. Yeah, a small number is, I think it's about 2 root n. So if you have n vertices, you have about 2 root n. You can take about 2 root n vertices away, and this splits the graph into at least 2 pieces, and the pieces are not very big. Okay, so I think it's if it's 2 root n, the remaining pieces are not more than, I think, 2/3 the size, 2/3 n. Okay, so, and then you can recurse, because if you take stuff away from a planar graph, it's still planar. So the idea is you can take a planar graph, you can take the separator out, and it splits it up. Now, you can't do that with a general graph. Why? Because if you consider a clique, Well, you take vertices away. Until you've taken them all away, you haven't split up the graph. Everything left is still connected to each other. So why are separators useful? So we're gonna this divide and conquer, right? So this is let's look at the map of yeah. So I can share my screen. Everybody is happy. Good. I lost some people. I had 61 participants and I'm down to 59. Okay. So let's go to this. Right. So here is a map of Nova Scotia. Can everybody see my screen? Now I have to switch. I have to make this. Yes, good. Okay. So here now. Okay. So here, Nova Scotia is 3-colorable. I'm not actually totally sure about that. I'm just assuming like Pictou, Halifax, Colchester, and Guysborough meet at a point. Same with Yarmouth, Shelburne, and Queens, and Digby. I mean, Digby and Queens seem to meet at a line, but I haven't actually checked, but it looks like that's a point. Okay, so how would you count the 3 colorings of Nova Scotia? So it's not that hard to find a 3 coloring, to determine that it is 3 colorable, right? Like you would just mess around and it's fairly easy to find one. But now I'm asking you to count the 3 columns. So okay, so now I'm gonna share my whole screen. Okay. And I'm going to recognize quadrant leader. Okay. So if you brute force the solution, right? So this is not a nice way to do something. Oh, chat. What's going on in the chat? I don't program much, so it's okay, but yes, but you can see like nobody has a problem understanding this, right? Like you can see what I'm doing, and if I said, could you recreate this? If I shut this down, could you rewrite this? And someone needs it. I said I don't code. Okay, so this is not how you do this. So you can see what I'm doing is just running through these things in alphabetical order, and then when I assigned all of the counties a color, then I check the adjacencies. And I'm being lazy. I'm only checking the adjacencies I'm checking each edge with only one endpoint. Yes, I agree, it's ugly. So then, like, if you actually want to see this work, wait, I have to, okay, I go to desktop. And I think if I enter CMD, so then I can, oh wait, where did that go? So this is, so like if I hit enter, wait, this should work. Yes. Okay, there are 1,944 3 colorings in Nova Scotia. So I think you notice that it actually took it took like a few seconds. Now, actually, if I do that again, it's faster. So apparently it needs some sort of setup, but it takes, like, you can blink, right? You can notice that it's not instantaneous. So how many possibilities is that's actually running through every possible potentially valid 3 coloring. So it's running through 3 to the 18 possibilities. Now, but if we look at the map of Nova Scotia, why would you do that, right? Because as far as I can tell, Cape Breton Island is not connected. Now, I know there's a highway, but ignoring the highway, Cape Breton Island is an island. It's not connected to the mainland. So however many ways you can color Cape Breton Island, for every way you can color Cape Breton Island, and every way you can, so if you know the number of ways you can color Cape Breton Island, and you know the number of ways that you can color the mainland, then the colorings don't sort of interfere with each other. So how do you get the number of ways to color the whole province? You just multiply, right? Because if there are, I don't know, X ways to color Cape Breton Island and Y ways to color the mainland, for each of the X ways to color Cape Breton Island, there are Y ways to color the mainland. So it's X times Y, right? Okay, so that gets you down to only checking 3 to the 4 plus 3 to the 12. But 3 to the 12 is still, if you were doing this manually, it would be annoying. So let's use this separator theorem. We know since the mainland is the graph of the mainland is a planar graph, we can find a small number of vertices such that when we remove them, it disconnects the rest of the vertices in the mainland. So basically, we're going to find some vertices whose removal makes 2 islands, or at least 2 islands. Neither of these islands is going to be too big. So, for example, what if we choose Hans and Lunenburg? Right. So if we remove Hans and Lunenburg, then you get Kings, Annapolis, Digby, Yarmouth, Shelburne, and Queens. Actually, I think on the midterm last year, no, not on the midterm, because that was take home, but on something last year, I put a question of name the counties of Nova Scotia, because I'd made people do this, and I figured, oh, well, you might just, like, you learn some geography. And so it splits into the South Mainland, and then into Cumberland, Colchester, Halifax, Pictou, Antigonish, and Guysborough. I have since forgotten all the geography. I've been in Halifax for a year. I haven't been more than a 2-hour bike ride away. So you could keep doing this. For example, you could do it another level and say, oh, well, to count the number of ways to color the North Mainland, I could split it, I could remove Pictou and Halifax, and then I'm just counting the number of ways to color Colchester and Cumberland, and the number of ways to color Antigonish and Guysborough. So now the thing is, for each way to color the separator, you consider the ways to color the connected components that are made when you remove the separator, right? So let's see this in some code. Okay. And then we're just going to restart the camera. So let's see this. Oh, I don't know. So yeah, but it doesn't matter because you're going to get high resolution in the Zoom recording, at least of the screen shares. So let's see. Yeah, this is going to be kind of ugly too. I was having problems with my internet so I reset my computer like on Sunday or something, and so I haven't got anything installed. I had to reinstall. I haven't got a development environment or anything like that. Okay, so this is going to be a little bit faster. So what we're going to do is say, okay, I'm going to choose my separator is going to be Hansen-Lunenburg. And so what I'm going to do is for every way to color Hans and for every way to color Lunenburg, well, except that I don't want Lunenburg to be the same color as Hans, right? So I'm going to choose, I'm going to look at this separator, and then I'm going to count the ways to color the mainland. So if Lunenburg is equal to Hans, I can just stop there because it's not a valid 3 coloring because they're adjacent. And otherwise, what I'm going to do is say, okay, then I'm going to add to a counter the number of ways to color the North mainland and the number of ways to color the South mainland. Right? So notice, I know like the people who teach programming would hate me because I'm using global variables because I'm lazy. This is like a 200 line. This is, I don't know how many lines of line program it is, but so global variables like aren't going to kill me here. Okay, so what? How do we compute the North mainland? So well, we go through all of the things. Now here, I'm just doing brute force. I'm just going to go through in alphabetical order, even doesn't really, I mean, it's so small, it doesn't matter in this case. And I'm going to say, okay, Antigonish for all the colors, all the ways to color Antigonish. Antigonish doesn't touch Lunenburg or Hans, so I don't have to check anything. Colchester, all the ways to color Colchester. Colchester, I have to check that it doesn't touch Hans. Cumberland, make sure that it's not the same color as Colchester. Go through and say, okay, so I go through all of these and make sure they're not conflicting with the separator and they're not conflicting with each other. And if they don't, then I add 1 and then I return. So this is my function to count the North mainland, the number of ways the 3 color the North mainland, given a coloring of Hansen-Lunenburg. And then I do the same thing for the South mainland. And then also I do the same thing for Cape Breton Island. Okay, which is easy. So I'm just going to go to participants for a second and ask, how do I make this bigger? Stop share. Okay. Okay, I want people to think out, like, could you, now I posted both of these little code snippets on Brightspace, but if they weren't there, could you write this yourself? So I'm going to ask you to put up your hands. Could you, if I asked you to, now, yes, you can count the colorings of Nova Scotia. So 3 people could do it with a little bit of thought. Okay, so a separator, there are algorithms to find small separators in planar graphs. I'm not going to teach them to you because actually I don't know them. I mean, I heard it described that a separator, you'd sort of take the planar graph and you draw a line down it, and then you like try to pull stuff to either side until like the stuff is about half and half. And I love the way that the guy described it. He said this intuition is not entirely wrong. It's probably not entirely right, but yeah, okay. There are algorithms to find polynomial time algorithms to find small separators in planar graphs. But for this, you would just eyeball it, right? You just look at it and say, okay, I want a small set of counties such that when I remove them, then it sort of breaks Nova Scotia up into little pieces. So you don't have to remove anything to break up Cape Breton Island from the mainland. And then if you look at the mainland, you think, okay, how would I do a separator? If you drew it as a graph, you'd be like, well, here I can take these 2 out, and then it's sort of half and half. And then if you want to do it recursively, you'd be looking at the North mainland, and you'd say, oh, I could do, what did I say? You could do like pick 2 and you could do, yeah, if you remove pick 2 and Halifax, then you separate Cumberland and Colchester from Antigonish and Guysborough. Okay, so that's, if you look at the code, where is this code on Brightspace? Under assignment 1. If you look at the code, so let's just share the whole screen. If you look at this code, so this is the faster way. I'm running through, I'm assigning, these are global variables. I'm assigning colors to Hansen-Lunenburg, which are my separator. And then I'm calling count the number of colorings of the North mainland. And when I go here, when I assign a color to Colchester, I have to make sure it's not the same color as Hans. So notice that, so the North mainland, I'm having to check against the separator, but I'm never having to check against the coloring of the South mainland. I can count the North mainland and the South mainland independently because they don't touch, because if they did, it wouldn't have been a separator. Okay, so chat. Okay, so the this is I want you to I want to traumatize you. So like later in life, if anyone ever mentions divide and conquer, you think, oh, the colorings of Nova Scotia. I don't want you to think like, oh, divide and conquer, it's merge sort, it's only good for easy stuff. No, I want you to like, I want this to be burned into your memory. Okay. So what we've got, I'm going to stop share. So people could figure out like, okay, you can see that if you want to count the colorings of Nova Scotia, you can count the colorings of Cape Breton Island and count the colorings of the mainland. And then if you want to count the colorings of the mainland and you want to do it quickly, then you could actually say, well, I'm going to take out Hansen-Lunenburg, and for every way to color those, I'm sort of running out of time. I'm going to consider the ways to do the North and the South, and I don't have to. Ooh, somebody raised their hand. We can stop sharing, and then I can actually let somebody allowed to talk. You can unmute yourself if you want. Okay, or not. Or type? How? No, only the person who I unmuted. Okay. But maybe there's no microphone. Okay. Okay. I will. So you can type in the chat. Maybe. Okay, but so I will remute you. Let's see. So remember that if I do this with the naive algorithm, it's not slow, but it's slow-ish. And now let's now the thing is, remember the first time this runs, it takes a while. But if we do it fast, notice that I just type it and it's there. Are you seeing my screen? Oh, wait, I have to share the screen. Sorry. Okay, I have to share the screen. Okay. So people can see my screen, I hope. Okay, so if we do this with the naive method, like it's not slow, but it takes like a second maybe. If we do it with the fast method, it's just there. No, okay, that's the naive method. The fast method is like you just hit enter and it's done. Okay. So that's like, woohoo, like we spent half an hour, something like that. I don't want to remember how much time I spent last night, like writing this faster implementation to save all of like a second. But, so now we get to your homework. We have 15 minutes left. So how have I, so is this still, how is the battery dying already? I charged the battery yesterday, so it only lasts one lecture? Okay, so chat. They do make batteries like they used. Well, they don't make them like they used to. They're supposed to make them better. I'm going to complain to Jeff. What's his name? Jeff Hutton, the battery professor. Okay, so people can see this. So let's talk about your homework. So I'm not really using the board at the moment. So the separator. Oh, the recurrence. Right. I'm going to stop sharing. So if you've seen the homework, this is asking you to count not the 3 colorings, because actually it looks like that map is not 3 colorable. It's not obvious, but I changed the code to see if it could count the 3 colorings. It came back and said there are 0 3 colorings. So like in some maps, it's like, remember I drew, if you have, the example people usually use is if you're 4-coloring the United States, to show that it's not 3 colorable, there are actually there are some states down in by like California and Nevada where you have like 5 or 6 states, and you can check and see, okay, these are not 3 colorable. But I couldn't see an easy subgraph of your assignment, of the map on your assignment, that is not 3 colorable, but apparently it isn't. At least the code says it isn't. So maybe the code is wrong. I just wrote it last night. But the question is, how many 4 colorings are there? So there are 42 regions. So if you brute force it, it's going to be, and you do something really dumb, like you just run through all of the regions and try all of the possibilities, and then at the end you check and see if they're compatible. You will be trying 4 to the 42, which is, so 4 to the 5 is about 10 to the 3. So that's about it's like 10 to the 25 possibilities. So even with modern computers, it's not going to work by the time the homework is due. I don't think. It's not going to be like 3 to the 18, and it just finishes in a fraction of a second. I hope, because I want to actually make you do this with divide and conquer. Time complexity auxiliary. I have to start the camera again. Charge the battery. Oh no, the battery is dead. Okay. So this is bad because so I was testing this camera. Oh, so if I draw the recurrence, I'm gonna have to write it really big so that you get it in the Zoom recording. Oh, I have tea. I haven't drunk. So we have 10 minutes. So for this assignment, it's just going to be like, did you use divide and conquer? I don't even particularly care if you get the right number, as long as it's more or less right. Watch out for overflows. I found out that a long int is not long enough last night. So if you're getting a negative number, that's not the correct number of 4 colorings of the map. There are ways to check to make sure you're not overflowing. Also in C, you have to check before you do the multiplication and the addition. So the idea is you're just going to do sort of the same thing for the map on the assignment. You're going to sort of choose a separator, and you can do it recursively, or you can just like do it. And then you're going to take them away. You're going to, for all the ways to color the separator, you're going to check all the ways you can check all the ways to color the connected components. So I'm giving you this because you shouldn't be able to brute force it. So what's marked for the assignment is, did it run? Did it give you a reasonable answer? I mean, ideally we'll get the same answer, although I could also be wrong, because I just typed it in late last night. I'll check it. And the TA will just look at your code, write your code in some language that the TA understands. So ask the people that you have the emails. No, you don't have to use C. Like, I think, does everybody know Java? Like everything, I use C because it's closer to sort of what the machine is doing, and also because I've forgotten everything else. I knew Java. Everything I ever knew in Java is now deprecated. If I write in Java and I try to compile, the list of warnings is huge. Like I said, it's between you and the markers. To me, officially, algorithmically, all Turing equivalent programming languages are the same. So I don't care what you write in, but the marker has to be able to read it. So really all that's going to happen is get the code. Does your code compile? Does your code run? Looks at your code. Are you actually using divide and conquer? Is it looking? Does it look something like the second count the colorings of Halifax, only it'll be a bit more complicated. Yeah, so the recurrence. How will it be submitted? Anything special with a file structure? No, just submit your code and maybe an answer. So on this, you're allowed to work in groups. The thing is, because I don't, so yes, Brightspace has group assignments, but if I tell it that it's a group assignment, I have to tell it what the groups are. So then I have to manage how you divide yourselves into groups. I don't care. I don't want to know. And then if you want to change your groups, you have to come to me and I have to change it on Brightspace, and everyone is unhappy. So instead, it's marked that it's an individual assignment, but then the problem is, if somebody doesn't submit a file, Brightspace won't allow us to assign a mark. So one person submit, and we don't want the markers to waste their time marking the same thing 3 times. One person submits the file with everybody's name on it, and then all the other group members have to submit a text file, which has the list, the names and the banner numbers of the group members, all the group members. Okay, so that's why, yes, like submission is a little weird. I haven't set up the assignment on Brightspace yet because yes, you have a tutorial on Friday. And there will be office hours. We're still working out when we can do them. We think it'll be Thursday afternoon and Friday, like an hour or so. There's a conflict, so we have to be after the conflict. There's a conflict with another class, so we have to be after that. So it'll be like Thursday afternoon and Friday afternoon will be the office hours. So you'll have a tutorial on Friday, office hours next week. I just want to go over, in the 5 remaining minutes, I want to go over the recurrence. So, yeah, just so that I don't forget, where's the marker? Yeah. Where's the recurrence? Right, so what I told is, I told you that you can get a separator of size about 2 root n, right? So let's say that we're trying to figure out the time it takes to count the 3 colorings, the 3 colorings of an n vertex graph. So this isn't your homework. We're back to 3 colorings, because if I give you a planar graph, I don't know if there's a polytime algorithm to count the 4 colorings. It's not ruled out. I mean, there isn't a polytime algorithm to count the 3 colorings, because if you could do that, you could tell whether there was 0 or more than, or 1 or more, in which case you could 3 colorability, you could say yes or no. We don't have that. So anyway, okay, so you've got about, for each of these, about 3 to the 2 root n, then say it splits it into 2 pieces. They're each at most 2n over 3. So we're going to say this is about t 2n over 3. So this is just going to be an upper bound. And so this is in the notes. And you do some calculations, blah, blah. You sort of expand this out, and you get that this is 3 to the O of n 1/2 log n. Okay, so this is some constant times the square root of n times log n. That's not polynomial. 3 to the n to the 1/2 is not polynomial. So I'm going to switch back. Yes, one working. Okay, I have to answer these questions. These are about the homework, so this could be important. Yes, you have one working code per group. Yes, only submit one actual assignment per group. I don't know if you can see Zoom. I can see who's in the class. I would have to check and see if there's a way I can. You can on Brightspace. You can't on Zoom. Oh, okay. I don't want to say that I will send people an email with everybody's email, because this will be like, will like hate me for violating privacy, and we will have problems. They won't hate me as much as if like I threw exploding metal into buckets of water in front of the students, maybe, but it's still something I should avoid. So this is not polynomial time, but it is faster than so this, it's not polynomial time, but it is better than 3 to the n, which is what you get just trying every possibility, which is, as far as, I'm not sure if this is the best we have for 3 colorability in general. I think there's something, no, it's 2 to the n, I think is the best we have for 3 colorability. That's actually by a guy I know, I think, Mikko Koivisto. So we have only like a minute left. So the thing to remember is, remember last class I said, just because there's this, we think there's this river that separates the 2 parts of the forest, it's not like we can never go and play in the hard part of the forest. Your first assignment, you have to go into the hard part of the forest, not just say if there is there is a 4 color, you're actually counting colorings. Right, so counting the 3 colorings in Nova Scotia is harder than just saying if there is one. So, and it's not that hard in practice. There are things that they don't work in polynomial time, but they work well enough in practice. And even on small graphs, even stupid approaches, like that first code, that naive code I wrote, even that works in a second. So just because something's officially hard doesn't mean it actually is always hard. We don't just get to give up. So, and divide and conquer, yay, divide and conquer. Good luck. If you have questions, if you find discrepancies with the adjacency list, please email me. Otherwise, please go to the tutorial because, like I said, the tutorial next week will be for the homework after. Questions, comments, email me. Otherwise, we're out of time, and I'm not supposed to keep you waiting. So you can, anybody who wants to can leave. And I will stop the recording. Have I forgotten to say anything? No. Okay, maybe. Stop the recording. Have a nice day. I don't see you again this weekend. Have a nice weekend. Stay safe. Enjoy the spring. Yeah, you're not going to get a polynomial time algorithm. So just it has to run. I'm going to stop the recording. Yes, the